Welcome back to the AI Ascent podcast. And in this episode, we have Nathan Young, who wrote a paper titled Transformers as Approximations of Solomonoff Induction. Welcome to the episode, Nathan.
Pleasure to be talking to you, Luke.
So first, we can start out with some background questions about you, then we can jump into the paper. So first of all, where are you based out of and what degree are you pursuing?
I'm based out of Auckland, New Zealand. I'm doing a PhD at the University of Auckland.
Perfect. And why did you decide to study AI?
I did my previous degree in, it was called a Bachelor of Creative Technologies, which doesn't really mean anything. So I sort of got to the end of that and I was like, I kind of want to do something that's a bit more impactful. I've been reading stuff by, you might have heard of 80,000 Hours, the organization. It's sort of helping people to find. You haven't? They sort of try to help people do the most good they can with their career. And obviously one area that they're quite well focused on and have been for a while is AI, because obviously it has a huge potential to benefit humanity and bring about, huge increases in productivity, but also has the potential to go very badly. And I thought I'd be quite good at it, so I thought it'd be worth investigating, and yeah, just stuck with it.
Yeah. And how did you come across this idea for your paper?
Yeah, so the idea of Solomonoff Induction was one I was introduced to on a forum called Less Wrong, which is sort of dedicated to improving the way we think, combating biases, that sort of thing. It was introduced as a general solution to the problem of epistemology. Epistemology being an area of philosophy where try to figure out what we can know, what we do know, that sort of thing. So it's a very, vague, fiddly sort of area, but then it was presented this algorithmic general solution to that problem of philosophy. So I was immediately absolutely fascinated, and it's an idea that's stuck in my head ever since. And then I thought Solomonoff Induction, which we'll get into the details of that later, but it's sort of the absolutely perfect, ideal way of predicting a sequence, which is exactly what large language models do. So I thought, well, if it's the absolutely perfect way, maybe the state-of-the-art way of doing that is the closest to the ideal. And no one had appeared to have thought of that before, as far as I could tell, so I thought I'd write up my hypothesis in a bit of a literature review and publish that.
Yeah, this was a very interesting paper. This is the first paper that I've really seen that kind of combines philosophy with the potential for AI. So it was a very interesting read. And so what was your role in the paper?
Well, the short version is I wrote it. There are two authors listed on there. One is, the first one's me. The second one is my supervisor, who, at first I was like, do I need to put my PhD supervisor on all my papers as a co-author? I decided his contributions in our discussions were enough to warrant co-authorship, because this was just a write-up of, hypotheses that we've been generating for a while. But he only had an input to the ideas. The paper itself was written by me in one day, actually. I left it till the very, 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 very last minute. I sort of knew what I wanted to write, and then it was the absolute deadline for the conference I wanted to submit it to, and I just cranked it out.
Yep. And so that leads into my next question. Are you going to present this paper at a conference?
So I actually did just this last week. Just a few days ago on Tuesday, which would have been Monday for you in America. I presented it at a conference called ICONIP, the International Conference on Neural Information Processing, which was held just here in Auckland. And my supervisor was one of the organizers for the conference, which is sort of how I heard of it and thought, okay, this would be a good one to go to, because it would be relatively easy to attend. among other things.
I see. All right. Yeah, let's start talking about the paper. So, at a high level, what exactly is Solomonoff induction?
Yeah, I'm not sure how to pronounce Solomonoff either. I've basically been guessing. So, Solomonoff induction is sort of an idea that I've had to summarize a lot over the past year or two. It's a little bit difficult to do in sort of a paragraph, but I'll do my best. So, what it is it's an algorithm for predicting an arbitrary sequence. So if let's say you have an alphabet of just 0 and 1, just a binary string, like 0, 0, 1, 1, 1, whatever. Given what you have seen already of zeros and ones, how do you predict what sequence is coming next, or what character is coming next, and what comes after that, what comes after that? Obviously, there are a million ways to solve that. That's sort of why it's presented as a problem of epistemology, because which I tend to talk about zeros and ones being fed into this thing, but you can think of it as any kind of information being fed in, including, say, sensory data from your eyes and ears and nerves being fed into your brain. And the way that is presented as an ideal way of predicting what comes after any arbitrary sequence is to have what we call a Bayesian mixture over every single possible program that can, well, there are sort of a few different ways of thinking of it, but the way I deal with it in this paper is every single program that can write out what we've seen so far that will continue to output something. So say if you have the string 0, 1, 0, 1, that could be alternating, or that could be totally random, or that could be the beginning of an ASCII string. It could be a million different things. And so basically you just consider every single possible program that could output that. Obviously, you can't put equal weight on every single one of those, or it would be, what's the weight of this one program? It's, some finite number over a total of infinity over every infinite possible program. So the way that you weight them is by simplicity. In the ideal, you consider what's called Kolmogorov complexity, which is just sort of how complex a program is. But you can also consider it as input to what we call a universal Turing machine, which is basically just a computer that can simulate any other computer. So if you input maybe 0, 1, 1 is the prefix that you need to put into a computer to make it simulate an alternating 0, 1, 0, 1 program versus just 1 would be random, then we'd give more weight to the random program because it has a shorter, simpler code. And then as you see more characters in this ongoing sequence, you eliminate the programs that have failed to correctly complete the data. And eventually, the predictions that this Bayesian mixture will make, updating on successive characters in the sequence, the amount of prediction error that it makes this is a bit, might be a bit counterintuitive to understand at first. The amount of prediction error it will make, which can be measured in bits, will be no more than the Kolmogorov complexity of the program being used to generate the sequence itself. So the way that you measure a prediction in bits is, well, consider that random program, right? That will assign a probability of 50% to a 0 coming next and 50% to a 1 coming next over every character that could be coming. You take the logarithm to base 2 of that, that's obviously -1. So we'll make an error of -1 over every single character there. Whereas the alternating program, if the sequence that we've seen keeps being 0, 1, 0, 1, 0, 1 forever, it'll give that a probability of 100%. Logarithm to base 2 of 1 is the same as anything. A logarithm to base anything of 1, which is 0, because anything to the power of 0 is 1. And so that will basically count as making absolutely no prediction error, which is to say it's predicting the sequence absolutely perfectly. So as that goes on, despite the random program being simpler, the alternating program will be predicting it much better, making 1 bit less of prediction error on every single character. And so if the sequence keeps being 0, 1, 0, 1, 0, 1, 0, 1, the alternating program will quickly overtake the random program and also every single other one because it's predicting it absolutely perfectly. So it's losing absolutely no, it's making absolutely no prediction error. I hope that all made sense.
I see. Yep. And so what are unbounded solutions? How do they relate to chess playing algorithms? And then how do they relate with Solomonoff?
Yeah. So Solomonoff induction is what we call an unbounded solution, which is essentially a solution to a computational problem that just doesn't take into account time or space limitations. So any, you might have heard of the P versus NP problem, where there are some problems that are easy to check but not easy to solve. But once you know how to solve a problem, there's sort of a sense in which you understand it. You know what a solution to that would look like. So obviously, when you're taking into account every single possible program that could be predicting any sequence that you've been given, obviously that's going to take up infinite memory, and executing every program to see how well it predicts that sequence is going to take an infinite amount of time. So we imagine that it's being executed on, the technical term is on a hypercomputer, which is just a computer that can perform any finite computation in 0 time and has infinite memory. I sort of like to think of it as just a magic computer that can just do whatever I want. I like the term magic computer because it just emphasizes that this is not a real thing. It is not something that can exist in a finite physical universe, but is still a useful mathematical idea. So you mentioned chess playing algorithms. This is an example that I read in the post on the Less Wrong forum, which was written by Eliezer Yudkowsky. He gives the example of chess as a useful studying, a useful case study for unbounded algorithms. He first gives the example of an argument made in the 1850s that chess is incomputable by Edgar Allan Poe. The poet genuinely wrote an argument that in modern terms would be recognized as being that chess is incomputable. In fact, he even references Charles Babbage's analytical engine as the sort of thing that could never possibly play chess. Obviously, he was wrong about that. The reason he was writing that was because he was trying to prove that the Mechanical Turk, which was a machine that was supposed to be able to play chess, was actually being operated by a human, and he turned out to be right about that. But he was wrong that chess is incomputable. He thought that an algebra problem, one step follows from another with absolute certainty, so a computer can do it step by step. Whereas in chess, you don't know what move your opponent's going to make next, so you can't prepare for it. Which, of course, is wrong. You can consider, what will I do if my opponent moves his pawn here? What will I do if he moves his queen here? What will I do if he... And then you can plan sort of conditionally. But he sort of did recognize the hard bit, which is, the branching factor. If there's, 10 moves your opponent can make on the next turn, and 10 on the turn after that, and after that, and after that, it quickly branches out to the point where there's more possible chess games than there are particles in the universe. So about 100 years after Edgar Allan Poe said a computer can never possibly play chess, a famous computer scientist called Claude Shannon, who also invented information theory, proposed an algorithm that could play chess absolutely perfectly. Basically just by exploring the entire game tree, basically every single possible chess game, and figuring out what ideal endpoint you want to get to, which move will basically force probably force a draw. We don't know exactly how a solved chess game will turn out. Again, because the game tree is so large. But once we had that algorithm that could play chess, if we ran it on a magical computer that could do anything instantly, that was a huge advance from not even understanding really the problem and thinking, I don't know how to solve chess using a computer, so probably it can't be done, to, okay, it can be done. This is how it is done, ignoring time and space limitations. That was in 1950 that Claude Shannon proposed that, and it was in 1998 when Deep Blue beat Garry Kasparov, so a computer beat best human at playing chess for the first time. So it took almost 50 years for those, between having an ideal solution that would work if we could run it to actually having one that we could run on a computer that we had. So it's important to remember that once you have an unbounded solution to a problem, that does not mean that you've got a practical solution to the problem or anywhere near, but it does give you something to measure against. And so Solomonoff induction is that, but for sequence prediction, which could be, I don't think there are many problems that you can't turn into a form of a sequence prediction problem. But certainly things like what we give to ChatGPT, take this prompt and then this question and then produce a good response to it. That's an example of a sequence prediction problem where you'd want to measure the performance of any practical algorithm against an ideal, and that ideal within a set of limits. It does always make some error, but the error is bounded to the complexity of what you've been given already, of the whole sequence rather. So yeah, that Solomonoff induction is the standard that we can measure all practical large language models, which transformers are the basis of, against.
Interesting. And in the paper, you hypothesize that transformers can be modeled as approximations of Solomonoff induction at test time specifically, while stochastic gradient descent approximates Solomonoff induction during training time. Could you explain what you mean here?
Yes. So, yeah, the theory is that because transformers as the basis of large language models are the best we have at the problem of sequence prediction, that they should be the best approximation of Solomonoff induction in the way that Deep Blue was an approximation of Claude Shannon's original chess algorithm. But of course, it doesn't quite work that way, because a Solomonoff inductor, you wouldn't need to train a Solomonoff inductor. Basically, you could just give it the sequence of a prompt and a question, and you could just run it like that, and it would produce a response that's not necessarily better than ChatGPT from the viewpoint of OpenAI. OpenAI doesn't always want to make the best prediction of what a human would say. It sort of wants to predict what a very friendly AI that doesn't say anything offensive or dangerous would say. But it would be more accurate as a response. The response that Solomonoff induction gave relative to a large language model. So we have to consider the role of what a transformer does at test time. That is, when it's given a block of text and asked what comes next. And then we have to consider what it does at training time, which is when it starts off as a totally random, huge amount of matrices with random floating point numbers, and is given however much data. I don't know how much OpenAI has at this point, but a crawl of the entire internet and then some, basically. So yeah, stochastic gradient descent, which is the way that most transformers are trained, will be a way of taking whatever programs are randomly jumbled up in the initialization of a transformer and promoting the programs that will predict, whatever's in the data set that it's been given. And that will eventually, promote programs that obey English grammar and French, German, Chinese, whatever other grammars are in the data set, that understand all sorts of concepts that are mentioned in the data set. And then once it's got a good Bayesian prior over every program that predicts what's in the data set well, it then is given a question like, I don't know, what's a question you might ask ChatGPT? Write an email to tell my boss I'll be late for this meeting. Then it has to forget about 99.9% of what was in its training data set and promote programs related to work and professional language and writing emails and things like that to produce a good prediction of what an email to a boss might look like. And so those are obviously going to be a bit different, right? The way that a stochastic gradient descent neural network training will approach Solomonoff induction versus the actual performance of the neural network, those are going to be quite different, but I think there are ways that you can look at them as both approximating the same thing. One way of thinking of it maybe is that this is a limited Solomonoff inductor that has the entire training data set as the program. So it's read the entire internet and then please write an email for my boss. And those are being both updated on, but in slightly different ways.
I see. Very interesting. So in the paper, you mentioned the idea of splitting key parts of a transformer into separate programs for improved performance and explainability. Can you elaborate on how this approach might work and what benefits it could offer over traditional transformer models that operate as inscrutable matrices?
Yeah, so the theory is that if a transformer is approximating a Solomonoff inductor, which is a mixture of all prior programs, that probably different parts of it, and these could be different parts as in different neurons or different groups of neurons, or maybe different weights within the same neuron, could be approximating different programs. And so, I mean, the absolute ideal would be that we could decompose it into something like a Solomonoff inductor, where we take out the program that predicts patterns related to what I was saying before: professional language, email writing, telling people you're going to be late to a meeting, all the I want to say something like billions, but I don't think that would even, I'm not sure that would suffice as to the number of programs that you could theoretically get out of a transformer. B, I don't want to have to put an upper limit on that, although I may have to. The ideal would be taking every single program like that, making it into a more, either an explicit program or a smaller set of neurons that are ignoring all the other, the other activity going on in the transformer. And that might be that might help to understand what's going on in a transformer, because you can see which programs are immediately going, oh, my job is to predict facts about crocodiles, so this prompt about writing an email is I've already failed to predict that someone would want to request an email, so I'll just put a very low prior on. Sorry, I've lost my train of thought. Sorry, could you repeat the question? I think I missed the second part. The second part of that.
Yeah. Can you elaborate on how this approach might work on creating separate programs for improved performance and explainability compared to the traditional approach with transformer models, which operate as inscrutable matrices?
Yeah, so at the moment, transformers do operate as inscrutable matrices, right? You've got these huge fields of numbers that are making some neurons fire and some not fire, but so if you can decompose it into an explicit program, obviously it'll be easier in a sense, right? If you had an actual Solomonoff inductor, I think it would be easier to interpret than a transformer, because you could have a model of what each machine is doing. But you do run into the problem that even if you're given a Turing machine that has, even if you're given a complete definition of it with a certain number of states and a transition function and the start and end states, it's not necessarily very easy to tell what that's doing, but it's a lot easier than investigating a matrix, because, well, one, it's more well studied. Turing machines have been studied since since Turing first proposed them, but more to the point, computer programs in general are something that human beings find a lot more intuitive than creating matrices, because it's something that can be that we can wrap our heads around and design. No human has ever designed a set of matrices for solving a program. You can train matrices, but you can't really design them for anything as complex as predicting human language. So the hope is that if you can deconstruct a transformer into something more like a Solomonoff inductor by isolating different patterns or different programs, that would be easier to understand if it was more like a traditional program than a field of matrices, because it's just not aligned with the way humans think. Whereas, explicit programming is more like the way humans think. Although, as anyone who's ever been given a program to fix knows, it's not obvious to. It's not a trivial task to take a block of code and immediately understand what it does, but it's at least a lot easier.
Yeah, definitely. So also you mentioned that transformers and neural networks can emulate arbitrary Turing machines. How does this universality shape the way we think about their capabilities and potential limitations?
That's a great question. So that's a large part of what made me think this might be a theory with some meat to it, because if you're considering all inputs to a universal Turing machine being able to predict arbitrary sequences, it's also the case that a neural network, or most kinds of neural networks at least, and transformers, which have been, their computational properties have been quite well studied, they can approximate, or rather they can exactly emulate, any arbitrary Turing machine. Now that comes with a few asterisks. The first one is that in most approaches, at least, it requires infinite precision in their memory. A Turing machine, in its ideal theoretical form, will have an infinitely wide tape, whatever form that takes, that it can write on indefinitely. And so in order to guarantee that a transformer can do anything that a Turing machine can, you need to give it some way of storing arbitrary amounts of data during its computation. And so the way that's normally done, not just in transformers, but in most neural network emulations of a Turing machine, is by making it store that as the value of a neuron, right? So a neuron might have a value of, well, a value that's between 0 and 1, but the way that it stores data is by making the decimal expansion of it, something like 0011001, whatever, and so on to arbitrary precision. That is the way that it approximates the infinite memory of a Turing machine. It's by having infinite precision in weight of a neuron that can store a number between 0 and 1, but by having infinite precision to an infinite number of decimal places, it can store a sequence of binary numbers, basically. Or sometimes it's in a different base than binary, but the point remains the same. And so, obviously, that's not actually possible. Firstly, because every computer ever made has finite memory, but more to the point that most implementations of a transformer will cut the the value of a neuron down to some amount of decimal places, which tends to be all right in practice. But it does mean that, in theory, it's not perfectly able to emulate any Turing machine. That's generally all right. And so the way that a transformer might approximate Solomonoff induction is by emulating sort of multiple Turing machines at once. That's sort of the idea. It's that it can, if it can emulate one Turing machine, it can also probably emulate multiple, in sort of parallel. Sorry, I've again forgotten what I think was the second part of your question.
So yeah, how does this universality of how neural networks can emulate arbitrary Turing machines shape the way we think about their capabilities and potential limitations?
So if a transformer can emulate any arbitrary Turing machine with, again, an asterisk or two, that does in theory mean that it is capable of predicting absolutely any sequence at all. It means that no matter what data you give a transformer, it should be able to learn it and predict it. Although, again, that memory limitation means that there is a limitation in how well it can approximate a Turing machine. This comes in relevant in a bit where I discuss in the paper how well transformers can. This is a paper by some other people where they investigate how well transformers are trained on, how well they perform when trained on different tasks in what's called the excuse me, in what's called the Chomsky hierarchy. That is, it was originally proposed by Noam Chomsky as a way of classifying different grammars. Chomsky wanted to make a universal way of telling whether an English sentence is valid or not, or a sentence in any language is valid or not, by saying, okay, if you have a noun and then a verb and then noun, that's okay. This is if you have an adjective and a noun, that's a noun phrase. Creating all these rules that eventually will create a valid sentence. And so he put different kinds of grammar rules into 4 different classes that end up correlating very well, not very well, exactly, with the kinds of languages that are recognizable by different computational schemes. So one of those is type 3 grammars, which are called regular grammars, which are recognizable by, I was taught in my first year computer science class that you recognize it with a finite state automaton. That is correct, but another thing that can recognize any of those types of languages is a regular expression, which I would think most programmers would be quite familiar with. If you want to recognize something like, say, an email, you say, okay, this should be a string of alphanumeric characters, and then an @ and then more alphanumeric characters, and then a dot, and some more alphanumeric characters, and then that's the end of it. And that will be an email address. There could be more dots and alphanumerics after that, but the point is that it's a relatively simple sequence that doesn't require any memory. A finite state automaton has no memory. A regular expression has no memory. And so when you train a transformer on tasks that fall into that category, it does better than if you give it ones that require more memory. So going up the Chomsky hierarchy, there's what are called context-free languages, which can include a string of zeros followed by a string of the same number of ones. You can't have a regular expression recognize email addresses where the bit before the @ is the same length as the bit after, because you can't have it referred back. But you can if you give a finite state automaton a stack, making it a push-down automaton. That's the kind of automaton that can recognize the second class of grammars in the Chomsky hierarchy. The very top of the Chomsky hierarchy is what are called recursively enumerable languages, which are those recognizable by a Turing machine. And those are the ones transformers do worst on. So even though a transformer is capable of emulating any arbitrary Turing machine, that asterisk that it doesn't actually have infinite memory does seem to make it perform worse in practice. So when you say a transformer is capable of doing, predicting absolutely any sequence that is given, it turns out that that is not quite right. That is sort of a price you pay for having an algorithm that is possible to compute on an actual computer versus on a magic computer like Solomonoff Induction. So it does imply that transformers' capabilities are not universal necessarily. It does give them some form of limitation, although it's hard to get a handle on what that is from a computational point of view.
Very interesting. And so next, you mentioned some practical limitations like finite memory and precision in how neural networks emulate Turing machines. How do these constraints shape the design and use of neural networks in real-world applications?
I mean, from my perspective, they sort of don't. I haven't encountered a lot of... I'm not sure where I would encounter this, but you don't see people talking a lot about what AI is not capable of doing from a practical perspective. Like, transformers are worse at doing tasks that require arbitrary rewritable memory like a Turing machine, as opposed to ones that are simpler. But they do still seem to be able to learn it in practice. At least, even if they learn it more slowly, they do still seem to be able to learn it. So the design, I'm not really sure how it would impact the design. I would think there's a possibility that by increasing the amount, increasing the amount of precision that a neural network operates to would increase its precision. I mean, it would have to have a positive effect. But I wouldn't think that the amount of memory that would require would be better than something like just increasing the width or the depth. People don't seem to want to give neural networks the ability to track floating point numbers to, well, not floating points, but numbers to an arbitrary level of precision. They seem to just want to make them bigger. That seems to be a better approach to making them able to predict sequences in practice. And that can help. By getting two neurons, you do sort of increase the number of the number of decimal places, which is to say the number of emulated Turing machine tape cells that a neural network can remember. It does double it, but it also increases their computational power by just making the neural network bigger. Which does seem to be, I mean, I don't think we've hit the limit in how big you can make a large language model before it starts getting worse. The constraints at this point are much more economic and physical than computational.
Very interesting. All right, next, what might be some areas of future work that could be built upon the ideas in this paper?
That is an excellent question, and one I've been working on trying to answer for a while, to the point where my supervisor said, look, you're sort of chasing too many different potential thesis chapters at this point, Nathan. You need to concentrate on one or two. So so I've got a few in mind. You did mention before decomposition into very purpose-built programs from giant inscrutable matrices. There are already people working on this. I'm not sure they're doing it from a... I would think they're certainly not doing it from a perspective of trying to make Turing machines per se, and that's probably all right. That's probably a... Turing machines were invented almost a century ago now. They're not the most... they're not the best computational scheme that we have, and they may not be the one that transformers can be best modeled as using. In the paper, I suggest that even though a transformer is capable of emulating a Turing machine with a finite amount of memory, of course, like I said, it is better at simpler tasks that require less memory, so it might be more fruitful to try thinking of transformers as a Bayesian mixture, not of Turing machines, but of maybe some finite automata and some finite automata with a stack, a pushdown automaton, and different programs on the Chunksy hierarchy. So there are a lot of different ways of decomposing a neural network, neural networks in general, but also transformers. That's one potential direction. That's another thing that almost every part of my argument that transformers approximate Solomonoff induction applies equally well to neural networks. Short, smaller, simpler neural networks are also capable of emulating any arbitrary Turing machine. To build a universal Turing machine with a recurrent neural network only requires about 1,000 neurons, possibly a lot fewer. But the question is, why are transformers so much better? Large language, you can't make a large language model out of something like a recurrent neural network or a convolutional neural network. And so that does sort of raise the question of why. Saying that they're better is sort of equivalent to saying that they approximate Solomonoff induction more exactly. So if transformers are better at approximating Solomonoff induction, that is to say, better at sequence prediction, which they do seem to be, why is that? Is there something in their structure that is better suited to approximating different programs? Do they have some sort of architectural thing that other neural networks don't, that make them better to approximating Solomonoff induction? If so, what is it, and how can we use that to interpret them better? And also, if not, if this all turns out to be gesturing at the wrong sort of thing, I feel like that would you'd be justified in asking why. If transformers aren't closer to Solomonoff induction, then why are they better? Because if they're not a better approximation of the ideal unbounded algorithm, that almost seems like saying they're not better at all. So that's one that I'm quite hopeful about, maybe more in the long term because it's a bit more complex, but definitely comparing transformers to other kinds of neural networks and also other kinds of sequence prediction methods under the lens of Solomonoff induction, I think would be really, really fruitful in explaining why they do so much better.
Very interesting. All right, and I know you were touching on this a little bit, but what's next for your research? Are you working on any new projects?
Ooh. I mean, I'm still yet to finish the meta project of figuring out what my next project is, but I did have an idea at the conference just this week of analyzing what a unbounded transformer might look like. There's some work into this in what an infinite transformer is, but part of the justification for investigating unbounded algorithms is that if you don't know what an ideal solution looks like, you sort of have no hope of creating an actual bounded algorithm, right? If you don't have Claude Shannon's algorithm, if you're dealing with Edgar Allan Poe's idea that chess can't be computable at all, you don't have no hope of creating Deep Blue. Then it occurred to me that very, very few people working in neural networks that I talk to have ever heard of Solomonoff induction. It's a relatively untalked about idea, which, as a form of general solution to epistemology, I feel like that's I feel like it's something that I would teach every second or third year computer science student, but maybe that's just me. Anyway, the point is that they don't have an understanding of Solomonoff induction or what a general solution to sequence prediction would look like at all, and yet they seem to do relatively well, right? People create neural networks and can predict language just fine because they understand how a neural network works and how it can gradually approach, predicting what it sees in a training set and apply that to a test set relatively well. So it occurred to me that people are sort of operating under working towards a different ideal than Solomonoff induction, even if my theory is correct and what they're doing is ending up approximating Solomonoff induction. They're trying to create a perfect neural network. And I don't know if anyone's done so much work into working out what an ideal training scheme. If you could train a neural network on a magic infinite hypercomputer, what would that look like? Some work's been done into that. But I don't think someone's created a explicit ideal algorithm and proven that this is the ideal performance that an LLM can approach. I think that would be very fruitful as a way of comparing a transformer's ideal performance to Solomonoff induction's idealized performance. How well would this infinite, or rather idealized, transformer do compared to Solomonoff induction? I'm not sure. I think that would be one potentially fruitful next project. It's one that's got a sort of a hold on my brain at the moment, so that's probably one I'll be looking into quite soon.
Very interesting. Great. That's all my questions. Thank you so much for coming on the podcast. It was really nice to hear your perspective and to hear about your paper. And I really enjoyed talking to you.
I enjoyed it too. Thank you very much for having me on.